to the cloud. Good afternoon, everyone. Today we will have a talk, another APAC seminar. This one is ideas. It will be a shorter version. Today we will have the talk of Joshua Graham, a brief introduction to algebraic K-theory and why it matters. Thank you, Josh. You can begin.
All right. Thank you, JV. Yeah, I'm talking today about algebraic K-theory, which as an overview is a kind of cohomology theory for rings. If you don't know what a cohomology theory is, that's okay. We'll kind of cover the main ideas so you can get a taste of what's going on. So as with any K-theory, if you ever hear K-theory, always think it starts off with something called a Grothendieck group. To give you the really basic overview of what that is, given a commutative monoid, it's natural to ask, what's the best way to kind of groupify this object, turn it into give it a group structure? And the way you do it, I mean, this is the exact definition here. If you want to get a feel for what it is, it's just a set of pairs, Mn in the Cartesian product of the two. And you can think of this, effectively as subtraction in the Grothendieck group. So you can have a bit of a play with this, and you can see that it does satisfy some universal properties. But intuitively, yeah, you can kind of convince yourself that this is the best way that you can kind of turn a monoid into a group. So as an example, if you take the natural numbers under addition, the Grothendieck group there would just be the integers. So exactly the same idea as earlier. You're just pretty much formally adding your negatives, your negative numbers. If you take any commutative domain R, say the integers, and yeah, R will become a monoid with respect to multiplication. If you take the Grothendieck group of this monoid, you'll get 0. And that's because you've included the 0 in your ring, and that kind of dominates everything else. If you get rid of 0, then you end up getting the multiplicative group of the field of fractions. So, I mean, if you take in the integers here and you kind of don't include 0 and you take the Grothendieck group there, you get the rational numbers except 0. So those are the really basic examples to give you a feel for what this is. Where it gets interesting is when you try and apply it to some more category theoretic structures. So if you have any ring R and you let this MR denote the category of finitely generated R modules, and we'll let PR denote the full subcategory of finitely generated projective R modules. If you don't know what a projective module is, it's just a direct summand of a free module. Then what you can do is form isomorphism. You can take as, I guess, the set in your Grothendieck group, the isomorphism classes of PR. And this is why we need them to be finitely generated. Otherwise, this isn't a set. And they form a monoid under direct sum in the sense described here. And the Grothendieck group of this monoid, we denote it as K0R, and it's the central object of study in algebraic K-theory. It follows from some other things in ring theory that this object is important, and so it's kind of natural to ask, like, well, how can we find out more about it? So as an example, if you take R a principal ideal domain or a local ring, then every finitely generated projective R module will be free. And so you'll have this isomorphism here. Effectively, the isomorphism is given by sending each class of projective modules to, I guess, the rank or the dimension. If on the other hand, R is a Dedekind domain, such as like the ring of integers in an algebraic number field, you get the free portion with a direct sum with the ideal class group of R. So in turning to like the topological K-theory side of this, you pretty much mimic the structure. And this is what started topological K-theory. So if you let K denote either the real numbers or the complex numbers, and you let X be a compact Hausdorff space, you can consider isomorphism classes of K vector bundles over X, and they become an isomorphism. It becomes a monoid under Whitney sum. If you're not sure what Whitney sum is, it's effectively just the pullback, but it parallels direct sum of vector spaces in many ways. And I guess a connection between these two constructions, if you let Cx denote the ring of continuous functions from X to K with multiplication and addition defined pointwise, then you can actually show that these two categories are equivalent. And so this is the connection between these two Grothendieck groups. So this K0 is the algebraic K0 we talked about on the previous slide. Last thing we'll talk about in terms of the Grothendieck group before we turn to looking at these higher K groups is how we talk about the Grothendieck group of an exact category. So effectively, there's the definition there. To talk about what it really means, there's I guess value in talking about a category with a concept of exact sequences, but you don't have all the baggage of an abelian category. Abelian categories need images, you need kernels, you need products, all a bunch of other things. In exact categories, we can have a concept of exact sequence without explicitly needing all those objects. Trivially, every abelian category is exact. But yeah, this is useful. I'll just say that for now. So as an example, PR, the finitely generated projective R modules, is an exact category. It's actually split exact in the sense that every exact category of projective R modules will split. In the sense that the middle term will be the direct sum of the outer two. Although it's a bit more difficult to show, you can also show that the K vector bundles also over X is also split exact. And the definition of the Grothendieck group of an exact category is we just take this KC to be the free abelian group with generators, the isomorphism classes of C, and we add one relation, A equals A prime plus A double prime for each exact sequence in E. So effectively, this middle term will just be the sum of the outer two. Yeah, I think, yeah, as if you kind of look at this long enough, you'll see that it's more or less motivated by noticing that these are split exact. And so maybe you think you should add these kinds of relations. And it's not too hard to see also, because these are both split exacts, that the Grothendieck group of them as exact categories agrees with the Grothendieck groups we've just mentioned for each of them. They don't in general agree. If your exact category is not split exact, yeah, they're not necessarily going to agree. And I've included an example at the bottom there. Are there any quick questions before I go on? Any things that I've kind of assumed too much of you? Otherwise, to talk about higher algebraic K theory, you need to have a good understanding of at least the history of topological K theory. So if you have an inclusion of compact Hausdorff spaces, Y into X, then by means of like a restriction on vector bundles, you actually obtain a functor going in the direction from X to Y. And you can actually show this will induce a map from the Grothendieck group on X to the Grothendieck group on Y. But we now define like a relative Grothendieck group, and we do it like so. If we let gamma XY denote the set of triples, AB alpha, where AB is some K vector bundles over X, and alpha is an isomorphism on, I guess, their restrictions to Y. Yeah, so we define gamma xy to be that set, and we let exy denote the subset of what we call elementary triples. We just require, yeah, effectively the same as above, but A equals B, and H is homotopic to the identity map on the restriction. We denote the Whitney sum component-wise, and we identify these two triples. We say they're isomorphic if there are isomorphisms from A to A prime and B to B prime, such that this square commutes. So this is all squares of isomorphisms. And we replace an equivalence relation on I guess the isomorphism classes. That's a small typo there. We should say the isomorphism classes to be proper. We identify them two triples, sigma and sigma prime. I'm getting lazy because I don't want to write out three things, so I'm just saying sigma and sigma prime. If their Whitney sum, if the Whitney sum is isomorphic for some tau and tau prime in the elementary triples. It's a bit unwieldy to see for the first time. The moral of the story really is that you just define the relative Grothendieck group this way. And the really important part that I want you to remember is that if X is compact and Y is a closed subset, then you get an exact sequence. That this exact sequence is the key to everything here. That the entire point, I guess, of topological K-theory is how can we kind of extend this in one way or the other and form some semblance of a cohomology theory. So as a small notational technicality thing, for those of you who are familiar with this going forward, since this exact sequence only works if X is compact, it's not very useful, even though the definition does work for non-compact X. So we're going to make one small adjustment. We'll just set Kx. If we're working with a locally compact Hausdorff space, we'll just define Kx as the relative Grothendieck group, where this X star is a one-point compactification and star is your point at infinity. And yeah, with this new definition, we'll agree if X is compact, and you can define the relative groups this way. And the important part that's really useful going forward is that you obtain this isomorphism. The relative group is just equal to the Grothendieck group of the difference. Since the difference will be locally compact if X is. So I'm not quite sure what the history of this definition is, but it was found that if you define the K of the negative n is just because we want it to be cohomological, but you can think of it as just a convention. We define it as looking at the K vector bundles over X times Kn. And we define the relative negative nth group to be the negative nth group of the difference. It's inspired largely by this. And with this, you've formed what's called an extraordinary cohomology theory. It's if you want, you can just Google it, but it's basically just a cohomology theory in which the cohomology of a point is not trivial. Really it just means you get a nice exact sequence in this way. And if any of you have worked with homological algebra before, you can kind of get a sense as to why you'd want something like this. It gives you much better insight. Well, it can help far more with understanding what this K0 group is, which I guess is a central object of importance in topological K theory. So the focus of algebraic K theory, now we've gotten that kind of introduction out of the way, is how you can use the tools that we've talked about here and apply them to rings. And the effort was largely inspired by the following. We let GLK denote, I guess, the group of invertible K matrices of any size, and you define it as a limit. So if you have, if you have, I guess, a matrix, you can embed it into a matrix of a larger square by just kind of adding a 1 in the bottom right corner and kind of padding out with zeros, and you can inform an direct limit in that way. It was found that this K-1x was isomorphic to the homotopy classes of maps from X to GLK with a group structure induced by matrix multiplication. And so with that, we thought, okay, maybe we should make K1R to be a group of classes of this GLR, exactly defined as this, but now we have entries in R, not necessarily in K. And so the way we did it was we effectively looked at these, what we call elementary matrices, these EIJR, for I not equal to J. It was though we just have an R in the ijth spot, 1s along your diagonal and 0s everywhere else. And you look at the subgroup, similar to how we do Gaussian elimination. We look at, I guess, the group generated by these elementary matrices to try and simplify your matrices. And we defined this K1R to be, the GLR modulo your elementary matrices. So again, you're looking at classes of matrices or classes of large matrices. I think we're running short on time, but that's not really important, that remark. It was also found that there was a nice way to define excision. So you need an excision if you want to talk about cohomology. And it was quickly perceived that you should have excision resulting from this kind of short exact sequence if I is a two-sided ideal. So we defined a subring in this way, and we defined the relative K group like so. The technicality of the definitions is not important. The important part is that we got a desired long exact sequence. Sorry, not long exact, but it's an exact sequence. Unfortunately, it doesn't really complete to 0 to the right, but nonetheless, for a homology theory on rings, this is looking pretty promising. A little bit, and it's worth pointing out that in some cases, this relative K group doesn't actually depend on R, only depends on I. But it's not always the case. So once we kind of found these groups this way, it was even more promising that this K1R had properties besides just being nice to chuck in a homology theory. And one of the main applications, as far as I can see, came through Whitehead torsion. So we defined the Whitehead group as this K1ZG modulo n, where n is the subgroup, the subgroup of units generated by this. We can think of this as just kind of ignoring our obvious units. And if you have a homotopy equivalence between finite connected CW complexes, it's natural to ask if this homotopy equivalence is simple. And what we mean by that is that you can kind of make it from adding, these elementary expansions and contractions on your space X. There's a technical definition for it, but you can think of it really as you add, say, like an N cell to X, and then you fill it out so you don't change the homotopy type. That's called an elementary expansion, and an elementary contraction is just going in the opposite direction. And so it's nice to know under what conditions will your homotopy equivalence be of this type. So we set this pi to be the fundamental group of the spaces, doesn't matter which one because they're equivalent. And we consider the induced chain homotopy between the singular, how you say it, the singular chains on the spaces. I'm omitting a lot of details here because Whitehead torsion is actually quite tricky to define, and I didn't quite understand everything. But what you get out of doing all the details and digging through all the maths is that you get an invariant, a homotopy invariant known as called tau f, and we call that Whitehead torsion. And the important part was that this tau f was 0 if and only if f is basically a simple homotopy equivalence. In other words, you can write f as something that's equivalent to a sequence of elementary expansions and contractions. So we had reason to believe that this K1R was useful besides just kind of being the little brother of K0 of R. K2 came a bit later with, I think it was John Milnor that originally defined it. But effectively, the patterns he noticed was that in this ER, these elementary matrices, you have these three relations, irrespective of the ring R. There are generally more, but they depend on the structure of R, and this is what K2 measures. What extra relations do we have here? So he defined what we call the Steinberg group now, and it was the group of words on these generators that will define these relations, but nothing extra. So you'll have a canonically defined homomorphism by setting these xij's to the corresponding eij, and you just define K2 of R to be the kernel. And it was found to extend the exact sequence that we showed earlier for K0 and K1 in a desired way, but it was very, very, very difficult to compute. As an example, the K2 of the integers is isomorphic to C2, and the only non-trivial kernel element you have is this thing here. It's very hard to find that this actually is in your kernel. Well, it's easy to show it's in the kernel. It's very, very difficult to show it's actually non-trivial. And this is the main tricky part with looking at the Steinberg group. If I give you some sequence of elements, it's quite hard to show if it's not trivial, if it can't be simplified to one. There was a theorem known as Matsumoto's theorem, which made it defining, finding K2 of fields a bit easier in some cases. And so you can show, for instance, using this, the K2 of F is trivial if F is finite. But moving along after we'd found K2 of R, we kind of thought, well, these definitions are getting a bit out of hand, so we need to have a more general description. And the first widely accepted description was using the homotopy groups of this space here. We just give K0 of R the discrete topology, so we're just taking K0 of R copies of this BGLR plus. So BGLR denotes the classifying space of GLR. It's just a connected space with all homotopy groups trivial, except for the fundamental group, which is GLR. And BGLR plus is a plus construction. Essentially what we're doing is we're just adding 2 cells to kill ER in the fundamental group, and then we just re-add 3 cells to make sure we didn't change anything in homology. So homology is the same, but we've completely changed the homotopy groups now. And it was found that the assignment was functorial in this way, and that this new definition of K3 agreed with our previous ones. And so if we have a 2-sided ideal, we also found that there was a space and a sequence of maps in this way, which induced a long exact sequence on homotopy groups, which gave us the desired properties. This is effectively induced by a CF vibration, or a homotopy vibration, if those of you who are familiar with that. We'll run low on time, but finite fields was pretty easy to determine with K-theory because of that reason. How do you say? The hallmark of algebraic K-theory would be the Q construction. Well, effectively, you extended not just to rings. Now we can extend it, the definition, to all exact categories. And yeah. I'm going to kind of run through the definitions now. But effectively, yeah, we were able to define this category called the Q construction, which took an exact category and it kept the same objects, but it would completely change the morphism structure within the category. And what we defined this new definition of K-theory was homotopy groups of this space here. And in particular, it was a major theorem when this came out, that we were able to show that these homotopy groups are the same, that you can extend K-theory in this way. And yeah, this is kind of a nice thing just to show that, yeah, things still work in the desired way. And with that, the main use of this was we could extend K-theory to schemes such that the K-theory of an affine scheme agreed with the ring K-theory of the underlying ring. But that's not really made any sense in the last probably minute or so, because I've desperately run to meet my time limit. So I'm going to apologize to the organizers now. But the main directions I've seen for the theory as of now, besides being a homology theory for rings, which kind of help you understand K0 better, is that you can generalize K-theory to Waldhausen categories, where you can show it satisfies some pretty convoluted properties. So you can go in that direction. Another one is that there's quite a bit of interest in trying to compute these groups. So one of them is via something called I think it's Hochschild homology. Someone will correct me if I'm not saying that right. But it's effectively another homology theory for rings. And so by comparing it to the K-theory homology, you can get a map which can tell you some information about K-theory. There's still quite a bit of work. We don't exactly know what the K-theory of the integers is. We're close, but it turns out that the Kn for n greater than 8 and a multiple of 4 is proving quite tricky at the moment. And yeah, of course, the one that's most pertinent to what I do is if you let this VBX denote the category of algebraic vector bundles over a scheme, it's effectively the same as topological vector bundles, but you're now looking at maps of schemes, not just maps of locally compact Hausdorff spaces. And you can define K-theory in this way, and it gives you a very nice way of finding Chow groups of a scheme, which give you rich information about how subschemes kind of lie in your scheme. With that, I'm happy to take any questions. Without going into too much detail, if someone wants to talk about K-theory of operator algebras, I'm happy to piece together something.
If possible, one question that I have is, what's the problem with the multiples of 4 when you're studying K-theory of the integers? Like, is it something explainable, or is it something that
I'll see what I can. I have a paper somewhere on my computer, but effectively there is a it's like a periodicity almost that repeats every 4. It's not quite like what periodicity that you get in topological K-theory, but there is a nice kind of sequence you see. It is conjectured that based on that, we know that K4 of Z is trivial, that because of this periodicity, it should be expected that K8, K12, K16, they're also all trivial. but we haven't, as of yet, had someone that can actually rigorously fill in the dots from what I've gathered.
Okay. Are there any other questions from the audience?
I'm waiting for Max to ask about operator K-theory.
I'm not going to ask about operator K-theory, but in general, how hard is it to compute, say, lower order K groups that you define here? For like just arbitrary rings, or is this difficult even beyond just basic rings?
It depends on what you mean by basic. K0 is, it's not too bad. It's really just a question of you trying to find like how do projective modules in this ring work. K1, for instance, I kind of hit a technicality in there. If you look at the Whitehead group of effectively trying to find K1 of ZG, that's absurdly hard. For two reasons. K1 as it is in general tricky to find for non-commutative rings. For commutative, it's a little bit easier because you have a determinant map, but it can sometimes still be tricky. And also the units, the group of units. If you want to understand K1, you need to understand quite well the group of units in your ring. And the group of units in an arbitrary group ring is also very hard to define explicitly. For K2...
Wait, sorry, what was that about? So if you take a ring to be the group ring of a group, then you're referring to computing K1 or K2 of that ring.
Yeah. So usually, as far as I know, what usually ends up happening is you'll have some sort of determinant map. Similar to how we define determinants in linear algebra. So these are really easy to find when R is commutative, which is nice. And if you define, I guess, SLR to be the kernel of this map, you of course get the expected short exact sequence. Or this should be the group of units. And in general, you'll have a map going back here, which kind of makes it all split. And so if you take commutators of everything, for R commutative, you get quotient out by ER, you get that this will be equal to the abelianization of the kernel, with direct sum with the group of units for R commutative. This doesn't work so nicely if R is not commutative. And in general, for group rings, for instance, you don't really even necessarily have this determinant map, so it gets even uglier. That's about the extent of experience I have with it. Most of the easy examples I know is just when you have some really simple description of this group. So for instance, if you have a Euclidean ring like the integers, you can actually show that this vanishes, which is about the best case you can get.
What happens if you have the continuous functions on a compact Hausdorff space? Can you put the K groups then?
I'm not sure. So yeah, the group of units there. I mean, you would have a determinant map because it's commutative, and your group of units is just all all the, I guess, the non-zero continuous functions. But here, this thing is not so easy to define. I'd need a bit more time to think about it.
Fun.
K2, because of Matsumoto's theorem, K2 is not too bad all the time for fields, but for rings other than fields, progress has been pretty slow from what I've read.
All right, thank you.
Thank you. So
And
sorry, I put too much in the slides.
nah, no problem.
It's on YouTube
And
now.
like we are beginning with almost the time for the next talk, so I will end up the questions for now. I would like everyone to thank the speaker for the talk. Thank you very much, and yeah.